from Humboldt postdoc fellow at Potsdam University. Currently, Dr. Valle is a FAPESP researcher at IAG, and her research is focused in modeling high-energy process in gas source. So today, she is going to talking about modeling synchrotron polarization in moving massive stars. So, Maria, thank you for being here with us. And questions can be asked after the presentation here on YouTube or on Google Meet. And Maria, is everything okay?
¿De qué tamaño queda? No consigo tirar. No consigo tirar.
Ele falou que no começo não estava saindo seu áudio.
Sim, porque... Mas esse vai sair. Porque esse está conectado. Hello. Stop. Okay.
So now we can go, Maria, please.
Okay. Thank you very much. So, sorry for this problem with the microphone. We changed the batteries and we are fine now. It's a pleasure for me to be here on the other side. Also, it's a pleasure to present my work for you. And I'm very grateful for the opportunity for sharing my work. So I am just going to share here. Okay, so can you see my presentation in Google Meet is fine? No, it's not? Okay, so I will just, yeah, that's okay. So I am presenting some work that I've been developing over the years, but today I am going to concentrate on one specific case that we are studying, that is the calculation of synchrotron polarization in runaway stars, or as I mentioned in the title, moving stars. So just let me introduce what is a runaway star. If we see a distribution of the spatial velocities of the stars in the galaxy, we can clearly see a distribution we can clearly see two populations actually. One population of stars moving with velocities less than 30 kilometers per second, here, and another population with less members moving at higher velocities, with velocities higher than 30 kilometers per second. So this shows us that there are some stars that are moving, and where are they moving? They are moving away, these runaway stars, they are moving away from the places where they were formed. We know that stars form all together, especially massive stars. So there are some runaway stars that we observe that are isolated. So then we check the velocity, and then we realize they are moving very fast, and they are moving away from their from where they were born. So there are two mechanisms that produce this type of star, of runaway stars. One happens in a binary system when one of the members explodes as a supernovae, and as a consequence, the other member would acquire a very high velocity. And the second one happens inside the massive cluster where these stars are formed. And there are under some conditions, some gravitational encounters can happen, and some members can be ejected also at high velocities. And we know that this is the channel that produces most of the runaway massive stars, and we know from simulations, and also we have some observations of this, that one massive cluster of stars can produce of the order of 5 massive runaway stars, and a higher number of stars that are not massive. So why massive runaway stars? Because there is a bias, observational bias, because the runaway massive stars, we can see them as they move. How can we see them? Because the massive stars, they have powerful winds. And as this star moves, it's the wind actually that is interacting directly with the interstellar medium. So we would have a collision of these two fluids or plasmas, that of the interstellar medium and the wind of the massive star itself. So during this interaction, here we can see your scheme very simplified. And if I am in the reference frame of the star, I am going to see the interstellar medium coming with a velocity minus the velocity of the star, and will collide with the stellar wind here. And in some point, the run pressure of the wind will balance the run pressure of the interstellar medium. The run pressure is the pressure of movement. Let's say it has this shape. So the point where this balance happens is called the standoff point. And this is standoff or radius. This determines a distance and a spatial scale of the problem. What problem, you might say? Okay, so the observation of this structure that is reduced through this interaction. When we have the interaction of these two fluids, we will have two shocks. Why? Because these runaway stars are moving at supersonic velocities in most of the phases of the interstellar medium, meaning that it will perturb the interstellar medium supersonically and will form two shocks. One shock, these two shocks happens also if we have two plasmas colliding. One shock will, in this case, one shock is the forward shock, the bow shock itself, that will propagate in the interstellar medium, and then the reverse shock, the wind shock, that will propagate in the wind. These two shocks, shock waves, have very different properties. The shock that is moving in the interstellar medium is radiative, meaning that it will lose energy through radiative losses, thermal radiative losses, and will compress the material. The other, and this is slow, with a velocity of the order of the velocity of the star, 30 to 100 kilometers per second. The other shock, the reverse shock, is very fast. It's adiabatic. So the radiative losses there are not efficient enough. And the velocity is very high, of the order of the velocity of the wind. I never mentioned it, but it's of the order of thousands of kilometers per second. So saying this, let's move on how we can observe these massive runaway stars. We can observe how they, as in many cases in astrophysics, we can see how these stars perturb the interstellar medium. And this is happening because as the star propagates and as the wind shocks the material and pile up the interstellar medium there, the interstellar medium has also gas and dust, and the dust is accumulated also in this dense, let's say, shell. And there is also the very strong photon field from the star, UV photon field. And we know that the UV photon field is absorbed by the dust present there. So the heated dust will then cool and will emit in the infrared. And we will see these beautiful coma-shaped structures in the interstellar medium associated, if we can see here, with a massive runaway star. This structure that we see, we call it the bow shock in the infrared. We observe it in the infrared. And I also would call the bow shock like the whole structure itself, okay? So please don't get confused. confused with that. So there are a lot of Bosch detected at the infrared. This is the distribution. You see, of course, we would find many of them in the plane, but we can also see others that are running away from the plane. So what is the deal with this? There is all this non-thermal thing or synchrotron thing of these systems started with the detection of radio emission from the ball shock of a massive runaway star, a very, very well-known massive runaway star with an observed ball shock at the infrared. So we can see here, this is radio contours that are almost invisible, but believe me that the shape of this radio emission is this coma shape, and here this map here, color map, is showing the structure in the infrared. So it seems that the radio emission is coming from there. And so after seeing this radio emission for catalog, dedicated observation at radio, 2 frequencies, discover emission that is associated with the ball shock. It has this, you can see, coma-shaped structure, and is showing negative spectral indexes. And just let me make a parenthesis here. In the radio continuum emission can be produced, and the most common channels are these Valle, Synchrotron, and Bremsstrahlung. And in radio, usually we can observe in only one frequency. So what can we do to see what type of mechanism is behind the radiation we are observing? So we can measure the spectral index of the observation. And for doing this, you can see we take the logarithm of this. We are able to measure, let's say, the spectral index if we have 2 frequencies. And well, sorry, I just jumped this. We can analyze the spectral index, and we can conclude that if the index is less than this value, the emission is most likely to be non-thermal. And so this non-thermal emission at radio is produced by synchrotron emission. Okay, so here I'm showing we have the 2 frequencies, and this is the spectral index map. And if we can see here, we have very negative indexes here that are that can be produced by synchrotron emission. And there are other ball shocks with radio emission, and there is another one that has been confirmed to be producing non-thermal emission, and there are 3 more candidates. They obtained 5 cases, but including these 2 here, of confirmed non-thermal emitters. So what is the big deal of having non-thermal emission? The thing is that we would have another channel for studying this system, because non-thermal emission is produced by relativistic electrons. In this case, synchrotron emission specifically is produced by relativistic electrons. So this is the implication is that we have a population of relativistic particles in these ball shocks of runaway massive stars, and there opens a lot of new questions and also other predictions. The existence of high energy electrons in the system can produce. Can produce emission at other wavelengths. So this is what the models are predicting. We expect non-thermal emission also at other at higher frequencies. And how is this happening? Well, we have the electrons, the high energy electrons, and in the sources we have matter, and we also have radiation fields, and we have also the magnetic field. And the non-thermal emission is produced when these particles interact further with these other fields there, the target fields. So most of the channels here that are predicting emission at X-rays and gamma rays are coming from the electrons. So is what we call leptonic emission. And there, we search also not only modeling pure pure theoretical modeling, let's say, we also search for some sources here, but we only have upper limits in some cases, but upper limits are very useful for constraining the parameters of our models. And we also have two candidates here that we find emission coincident with two very well-known also runaway massive stars with data from Fermi at gamma rays. Okay. I mentioned that the electrons are producing the non-thermal emission, and in our models is the favorite channel. And there are also protons, and we also consider this, and we conclude that the protons will escape into the interstellar medium, and locally they will produce an enhancement of the non-thermal emission there, and also an enhancement of high energy protons there. So let me go back to the electrons. Valle? Familiar? Okay, sorry for that. So another implication of the discovery of synchrotron emission on these systems is polarization. So just let me very briefly mention that if we have polarization, we have a preferent direction, or again, additional information on the direction of the polarimeter, and also of the direction in space. So polarization comes also with other ways or channel, let's say, more information to study sources. And why I mention this is because the polarization, we would expect other channels of polarization from ball shock of runaway massive stars. Because we have dust, and we know that dust can produce polarization, because the dust of grains align with the magnetic field, and this will produce polarization. And we also have polarization from Thomson scattering. And we also know that synchrotron emission, the emission that was detected at radio in some of these ball shocks of massive runaway stars, can have a very high degree of polarization. Okay, so the models predicts a degree of polarization of the order of 70%. This is a very, very high degree of polarization. So we aim to study and to model the polarization on these systems. And for the polarization, I mentioned we would have a very high degree of intrinsic polarization. However, there are a lot of physical processes that can modify this degree of polarization. And well, we have to take all of this into consideration if we want to have a proper model of the synchrotron emission polarization. Okay. I just mentioned briefly that we also consider the Faraday rotation, but you will see this more clearly in the results. So for the modeling, we have a three-step model for computing this, because first we model the interaction of the wind with the interstellar medium, including the magnetic field. So we perform MHD numerical simulations. Step two, we need to model the non-thermal electrons, because the non-thermal electrons are not the thermalized material of step one. These non-thermal electrons will produce the synchrotron emission, so that's why we need to calculate them. And the step three, the computation of emission, once we have the distribution of the electrons and the distribution of the magnetic field, the polarization, and the modifiers of that intrinsic polarization. So we simulate the wind of the star colliding with the interstellar medium, The wind, as I mentioned before, is of the order of thousands of kilometers per second. The velocity of the stars is of the order of 30 kilometers per second. And in this case, the velocity of the star is aligned with the magnetic field of the interstellar medium. Okay? So there are many models of this interaction that you can see. This is just an example. And one thing is that once we wait some time, the system will reach a steady state. And in that steady state, it is very probable that we will observe these systems in steady state, or at least some kind of steady state. So we will use the solution of this MHD simulation in the steady state. Okay. So I mentioned before that we would have the formation of two shocks here. One shock, the forward shock in the interstellar medium, and the reverse shock in the wind. So if we see a cut of the simulation in this direction, we can see these profiles. This in blue is the density, this in green is the temperature, and we see here, we can see here in the temperature a big jump here. This is the reverse shock, a very strong shock, and this here is the forward shock. That it has a typical shape of a radiative shock. So I skipped the part of the acceleration of particles because it would be too much information, but just consider that the acceleration of particles in shocks, this is diffusive shock acceleration, is more efficient in fast shocks. So if we have to guess where these particles, the relativistic electrons, are being accelerated, we are going to say, well, most probable they are accelerated at the faster shock, the wind shock. Okay, so this is hypothesis, and this is the hypothesis of all the models that are published. So the particles are accelerated at the reverse shock, where the shock is adiabatic and fast. So this is important for step 2, because in step 2, we are going to model the transport of these electrons. So for doing that, we solve the equation, this transport equation, diffusion and advection equation for the relativistic electrons. So we have, this is the diffusion, we would have spatial diffusion, and it's a power law in energy, this shape here, typical for the diffusion in the interstellar medium. And we would have the velocity and also the magnetic field and the density. We will have those from the MHD simulation. Okay, and we also have here the injection of the particles. So the non-thermal electrons are being accelerated and are injected at the position of the reverse shock in the simulation. Okay, so we solve this, and then we go to step 3, that is the computation of the radiation and polarization produced by the population of electrons that we calculated in step 3. Okay, so these are the results of the emissivity. This is synchrotron emissivity only. And we can see that in these systems, these are very big structures, and it depends a lot on the angle that we are observing this coma-shaped, large-scale objects. And the angle, we can think of the angle, at least in this case, as the angle that is making the velocity of the star, okay, towards us. So we can see that if we see the star coming towards us, of course projected in the plane of the sky, we will see a ball shock in this way, okay, in synchrotron. This is synchrotron emission. And if we have 45 degrees, we would have this one, and if we have 90 degrees, we would have this one. But we can have any angle, any projection that we want. Here I am showing this, and this is very important to bear in mind that these structures are 3D, so we had to take into the consideration all the directions, because what we would observe depends on this. Okay. So I didn't mention that here I am showing the synchrotron emission producing the structure in this frequency that coincides with the frequency of the radio detection. There were two frequencies I mentioned. We calculated in the two frequencies here, but I only shown this one in this plot. Okay, so we can see that the shapes are different, and this is also consistent with the shapes that we see in the infrared images of these sources. So this is the intrinsic polarization results for the, well, this is the other frequency, but the values are very similar. And we see this is the intrinsic without any modification. And we see a very high degree of polarization. You can see 50-70% in all the projections that I am showing here. However, we have to consider that this level of polarization would not be observable because there are other physical processes that modify greatly this degree of polarization. One of the most common is turbulence. We know that there is turbulence in the interstellar medium, but there's also turbulence in the system. This interaction between the fluid interaction between the wind and the interstellar medium is expected to be highly turbulent. Even though we cannot resolve the turbulence, it is there. So we have to put this turbulence by hand, but we have to consider it and to obtain a realistic value of the degree of polarization. So here, is without the turbulent component of the magnetic field, and we see 70%, and this is with the turbulence. So what we can see here is that this I didn't mention, but I'm mentioning here now. These contours are showing, indicating the regions where the emission is higher. When we are making a prediction, theoretical prediction, we have to take into consideration that when we do observation, we do not have we don't have we have a limit, a sensitivity limit. So we are not able to observe the whole structure. We are going to observe only the regions where the intensity is higher, and this is why these contours are shown. So the stronger the blue color, let's say, the stronger the emission is inside that region. So this changes a lot when we consider the turbulence, and it's only one modifier of the turbulence. This is a model that we consider these contours, but in the if we are dealing with a real source and a real observation, let's say, we would have the sensitivity limit given as those curves. Okay. So there is another effect that that's the effects on the polarization angle, and we see that I didn't put it here, sorry, that are produced by the Faraday rotation. In our case, Faraday rotation will change the polarization angle, so we will lose information because we would like to have information on the polarization angle when we observe the source, because I mentioned before that this would be a channel for getting information. But we see here that we have to be cautious with that because of the effects of Faraday rotation. Okay, and in our case, the effect of Faraday rotation is stronger inside the source, and I will come back to that later. I don't know if you can see here clearly, but I am showing here the direction of the magnetic field and the third direction for the polarization. They should coincide, at least. It depends on many things, but it should. But we see this is a higher frequency, and this is the lower frequency that we calculate. And we see here, you see there is a very high rotation compared to this one. And we know this is produced by the Faraday rotation because the Faraday rotation depends and is stronger on the lower frequencies. So we can still see another loss of information produced by Faraday rotation. Another thing that is contaminating the emission, at least the emission that we are interested in, that is the non-thermal emission, is the thermal emission. Because we have the star that has, don't forget, a very strong radiation field. And we know that massive stars, they can ionize the interstellar medium around them. And this can produce a region, ionized region, a very large ionized region. For this star, what we are modeling, the stronger radius of this ionized sphere of the interstellar medium is of the order of 75 parsecs. This is quite a large value if we consider that this here, that I'm showing here, is of the order of 16 parsecs, okay? And why this is important? Because if we have a ionized medium, it will emit through Bremsstrahlung emission or free emission. And this emission would be there also. And if we are observing towards this system, we would see everything together. So when we are calculating the polarization degree and also the radiation at radio, we have to consider this emission produced by the ionized region, okay? So consider that we can also see another effect, not also on the polarization, but also on the radio emission that we are going to see. So this here I am showing the synchrotron emissivity, and here is the Bremsstrahlung emissivity. We can see that it's very high, even though the regions where one dominates are different from one another. And this is good for us if we can observe the system, if we can resolve the scales of the system, because we would be able to see some of the synchrotron emission under the Bremsstrahlung. Okay? And so we can see that the contamination for thermal emission change further the degree of polarization. That's intrinsic degree of polarization. A lot. And you see here, bear in mind what we would be able to observe. This here, not here. So if we see here, the degree of polarization is very, very low. Lower than the effect produced by turbulence, at least in this system. That is not so dense, but I am going to comment on that later. What about the index, the spectral index? Well, we calculated the two frequencies. If we take the logarithm of the emissivity, we would have we would have the index computing only the differences here, okay? So we can make a map of that, and we see that it depends a little bit on the angle on which we are observing the system also. Everything depends on the angle that we are observing the system, or let's say the angle where the system is and we are looking at, okay? But we can see that we won't be able to detect, at least in this system, such negative spectral indexes that those that were observed in this massive runaway star that was observed. If you remember, I'm sure you don't remember, but it was of the order of -5, very negative. And here, if we can see, it's -2, -0.2, -5. But again, we won't be able to detect in this map this emission, or at least it would be very difficult. So we also have changes in the spectral index. And this change is mostly produced by the contamination of the thermal emission. Honestly, don't know how I am with the time. Thank you. And what about the background electrons? Well, we know that as we consider the emission produced by the interstellar medium itself, that is ionized, we know that in the interstellar medium of our galaxy, we have a background of cosmic rays, the sea of cosmic rays. Most of the cosmic rays are protons, but we also have electrons there. The electrons would also produce non-thermal emission, and will also produce synchrotron emission. Okay, and we also have to have this in consideration, because when we observe, we won't be able to take away the background electrons. They are going to be there, so we have to compute them all together to obtain the real signal that we are going to expect. So we also consider this, and we discover that the effects, if you can see, I think the numbers are quite big here, so you can see this map here is showing the synchrotron emission produced by the local accelerated population of electrons, our electrons, and this is produced by the background electrons, the cosmic ray electrons. Okay, so we see here that the values are comparable, but again, they dominate in different regions of the structure. Okay, so again, this is good news for us if we want to infer properties of the electrons that are being accelerated in the system, not the ones of the background. Okay, so we see here how altogether all the processes together that change our predictions on the polarization degree. These maps here is before all the corrections, and we obtain values of the order of those expected that I showed you before, expected theoretically. Very high degree of polarization, and usually when the people say synchrotron emission is polarized and the degree of polarization is very high, okay, yeah, but there are a lot of modifiers of this degree of polarization, and we need to take them into account. Otherwise, we are going to make a very bad prediction if we compare here with the final result, considering all these effects on the polarization. Again, we have to see here that for our case, this case that we are investigating, we won't be able to see a lot of polarization, or maybe any polarization. Okay. And this comes to study case. Everything that I showed you before is for a standard runaway massive star moving through an interstellar medium with a not very dense medium, that is with a density of 0.6 particles per cubic centimeter. Okay, even though it was not very dense, the thermal emission was very high. This is important. Okay. Again, we're coming back to this source that was observed at radio emission that I mentioned you before at the beginning, that started all this story of non-thermal emission in both of runaway massive stars. This, as we know that synchrotron emission is polarized, then there were dedicated observations to see if we can detect any of this polarization. And the answer is no. No polarization was detected, even though the signal in radio of this object is very strong, and it was detected 3 times in 3 different observations. So what is the problem here? And we believe that the problem here, that the thing why we are not seeing any synchrotron polarization here, is because the region is very dense. We have densities of the order of 9 particles per cubic centimeter. These are the inferred values in the local environment where this star is currently moving. And this is very high. Compared to that we were modeling, there was only 0.6 particles per cubic centimeter. So it's very probable that in this case, the polarization is completely under the thermal emission. And this is not new, because we know that there are other sources in which there is a synchrotron emission observed in some cases and not observed in others. And this is because the thermal emission producing the source is higher than the non-thermal emission. So the electrons, the high energy electrons might be there. This source might be able to accelerate the particles, but we cannot see the non-thermal emission because it's under the thermal emission. And it can be directly in the Bosch's structure, or it can be in the radius around the interstellar medium where this ionized sphere is there that I showed you before, the stronger sphere. Okay? So just to conclude, first, modeling the synchrotron emission and especially the polarized emission in this system is not trivial. We have to consider, I showed you before, 3 steps for calculating this. Each of the steps is non-trivial, and we also have to consider the fact that these are 3D structures. And the angle that we are observing these guys will change what we are observing, or the fluxes that we are going we will be able to detect. The intrinsic polarization is highly modified, as I mentioned you before. The radio polarization can tell little about the direction of the magnetic field, as I showed you before, because of the Faraday rotation effects, but also because we are observing, when we observe when we infer the magnetic field direction, we have to think that the magnetic field there in the point that is emitting the synchrotron is the magnetic field where the electron is, or where the electrons are. And the electrons are not distributed uniformly. And when we are observing this, we are observing the integration of this 3D object projected in the plane of the sky. So we are not really would be able to say so much about the direction of the magnetic field. Plus, we have the effects of the Faraday rotation. The polarization can shed light on where the particles are accelerating. Why? I didn't mention this, but I mentioned that one of the hypotheses is that the electrons are accelerated in the reverse shock, in the wind shock. And if you remember the region where most of the polarization is coming under this hypothesis is near the wind, because this is where most of the particles will be before they are advected in the wind. Okay? So if the particles are not, what if they are not accelerated in the reverse shock? What if they are accelerated in the bow shock, the other shock? It is possible. Maybe they are compressed there. We would have a different outcome for the degree of polarization and a different map, or a synchrotron map. So this is also a very interesting thing to consider and to extract from observation, if we have any, and also from our modeling. The contamination of free emission is important, and we can see that this is the most catastrophic effect that we can have in these systems, not only for the polarization, but also for the detection of non-thermal emission. And I also mentioned before that this happens in other sources, and these sources are colliding wind binaries. There are some colliding wind binaries. These are binary systems in which 2 of the stars have powerful winds. They collide, and they produce, during this collision, also a system of 2 shocks. These systems are believed to be able to accelerate particles there in these shocks. But there are very few, compared with all the systems that we know that are producing non-thermal emission, meaning that are able to accelerate electrons in this colliding region. But what is happening in the others is that maybe, they are accelerating the particles, but we are not able to see, because we will also have contamination by the thermal emission. Okay? If we're going back into a lot of slides ago that I mentioned that there were other cases where radio emission was detected by the Bosch's, but only a few were confirm of non-thermal emission. This doesn't mean that they are not able to produce non-thermal emission. It's that we are not able to see this non-thermal emission due to the thermal emission. And why is this important? Again, it's important because the high energy particles are there. We cannot observe particles, at least in this way, but we can see that if they are there, they are going to produce some effect around, as in the case of the protons that I showed you before. So I also mentioned the background emission. Again, if we are able to resolve spatially these systems, we will be able to tell, if we compare with models, where we would expect the emission from the background to be important or dominant, and that produced by the locally accelerated electrons. And also we have a problem here, because the brighter infrared sources, remember that we detect these guys at infrared. We first detect the bulk at infrared, and then we say, yeah, here we have a runaway star, here we have this colliding of the wind, etc. These systems are brighter if we have a very dense environment, because this will enhance the infrared signal. But these are not our favorite candidates for detecting non-thermal radio emission, because if we have a very high density, then we will masquerade the non-thermal emission. The synchrotron will be high under the bremsstrahlung. Okay, so we need more radio observations to compare the structure with our models. So thank you very much for listening. Está sin pilha. Vou fazer assim. Hoje está triste.
So it's really a very nice piece of work that you are doing here. You guys are doing here with all the details, all the mechanisms that you are taking into account. But I have several questions with regard to the setup of the simulations and the hypothesis of adding the ingredients. So are the simulations 2D essentially, or because part of the ingredients are one dimension? You inject profiles, right? For doing the, so what is the simulation itself? Is MAGD, it's 2D, or it's two-dimensional simulation? Okay, so, how do you account for the radiative transfer afterwards? Do you account for do you build the spot on field post-processing, or you do a profile, a one-dimensional profile? So this is one question. The other question is, why is that you have to introduce turbulence by force if the evolution of the shock structure by itself, both the forward and the reverse shock and the interaction with the interstellar medium, will drive naturally turbulence behind the shock and between the shocks. So behind both the shocks and between the shocks. So this is one thing that I do not understand, why you guys added turbulence afterwards, after you added to be MAGD turbulence, right? And the other question is, you solved the Vlasov equation also in post-processing, right? And how do you account for the cosmic ray propagation there? How exactly you did account for this? And how did you build the synchrotron and the bremsstrahlung? Only from the MAGD parameters? I mean, for instance, the equipartition with the pressure, then you get the synchrotron. So I'd like to understand more about the setup of the conditions. I
Is
can,
that very noisy?
I can ask again.
Okay.
I mean, you can answer by heart.
Okay, so the part of the turbulence, it's really easy to answer because we are not able to resolve. Is the correct word?
Why not?
Because we have a parsec structure, and if we want to, the turbulence is there, but it's not actually appearing because we don't have enough resolution in the simulation to account for this. And the way we are doing,
because you have this 2D simulation.
no, it's not because of that. It's because it's very high.
This is an important ingredient.
Yeah,
It's
yeah,
2D,
it's
you do not probe 3D turbulence.
okay. We learn how to put the turbulation from guys that do this, that make prediction on the polarization degree of sources in the galaxy. And even though if you have 3D simulation, you are not able to solve the scales of turbulence that we need. That's the first question. Second question is about how we deal with solving the equation for the transport of the particles. I show here. Yeah, these are only the profiles. We do not consider only a one dimension. We solve this in 2D because the system has symmetry. So we obtain we consider this diffusion coefficient, but we obtain for the simulation the magnetic field for computing the losses, and for the velocity field for the advection of the particles, we take it from the simulation, and also the density, the injection of the particles is a function of density because you would expect higher injection of particles in the denser region. So we also take this from the simulation.
What is the delta value that you have adopted? Fusion, or did you dependence with the distance?
No, we have here we consider 10 to the 26 as a normalization of the diffusion coefficient because we would expect that the diffusion is slower than in regular medium inside the region. The third one, the other question I forgot.
It is how did you evaluate? How did you compute the losses from?
The losses. Well, the losses are calculated here. The losses. But the once you take into account the losses of the particles, one, or you compute it directly, but anyway would be post-process because the emissivity, because you need the solution of n for the emissivity, so it doesn't matter. You can calculate it directly in the code or doing a post-processing. In some cases we compute it in the code itself, or in other cases we post-process, depending on.
But you did the radiative transfer mapping in 2D or 1D?
No, you need in 2D to do the transfer. Otherwise, it would make no sense because you need this structure. You need the whole dimensions.
But you adopted the symmetry.
Yeah.
It's very symmetry.
Yeah, axisymmetric.
Yes, the axisymmetric.
We are doing a 3D model for the. We are modeling the study case. So stay tuned. This one. This one. For this system that we have actual.
To see the absorption.
Because we have actual observation for this guy. So it's better to do it in 3D directly.
Thanks, Maria.
Oh.
I think two short questions.
Yeah.
They are connected. What acceleration law did you use for the outstack? Is it that law, Casper and Lambert, or something like?
Actually, we would expect the wind to be launched by this process because it's in this case I didn't measure it, but it's like O type star. So we would expect that would be the process of wind launching. However, at the distances that we are interested and also at the distance that we can resolve, the wind is already not accelerating anymore and it reached this V infinity velocity. So we consider just the radial source in the simulation, a radial source that is injecting wind with this V infinity the whole time.
Yeah.
And the loss, the mass loss rate here is quite moderate, let's say, it's 10 to the minus 7. While in this observed guy is like 10 to the minus 4. It is believed to be. So this guy is really, really powerful. That's why we observe, I believe, this guy and no others.
If you consider the terminal velocity, you may eventually see a correlation between the mass of the star and the properties that you predict.
Yes, exactly. Some people, like the ones that I showed there, Koblnicki and many others, they study the properties of both the interstellar medium or the star by measuring this infrared emission in the system. Because the point where the both pressure balances the interstellar medium and the wind, this kind of distance, you can measure from the observations. So having this, you can have an independent, let's say, measurement of the mass loss rate of stars. That is not depending on evolution models. So this is really interesting also from people working on stars.
Yeah, and a short comment is that if you scale your velocity by a factor of 10,
yes,
thinking about the amount of eruption and white dwarf, you have the same process already observed. You see non-thermal emission from like the accelerated shock.
yes, yeah. Actually, I made some modeling on that. We can discuss if you're interested.
Okay.
Hi.
First of all, thank you very much for this nice and instructive talk. We have a number of candidates of synchrotron sources in interstellar tests from massive stars, from spectral index measurements that are negative. We would like to prove that it's actually synchrotron measuring polarization. Although after the last slides that you were showing this one, I'm a little bit less optimistic, but I hope we have a candidate. So I was wondering if your model can be extended to a case where we have a very fast protostellar jet using a magnetic field in the stellar medium cloud. Obviously, in this case, these are also massive stars forming a very close environment. Densities are very high. Contamination from thermal quickly breaks down is very strong. So, after all you say,
yes,
I'm a little bit less optimistic, but would it be possible to extend this model?
Yes.
That was your question.
No, I have a question with regard to radio.
Yes, absolutely. You must search for this, even though with caution, meaning that you have to cherry pick your systems, but it doesn't mean that there is non-thermal emission there. Or even though, as I show here, if you can have a region solved, extend region, that I think would be the case, you can carefully check where you are going to see the non-thermal emission, where to look at, and where regions to look at. And also there are some very powerful sources that you can consider that are like HH8081, I guess, is a very powerful source.
Yes. Yeah, I have technical comments on this. Yeah, definitely, it's the physics is the same. So the same kind of model is applicable to massive protostellar jets and non-thermal. Nevertheless, as you mentioned, in the radio emission, the non-thermal region should be detached from the thermal emission. And one thing that we have to keep in mind, this is known for decades, that when you do simulations of radiative shocks in 3 dimensions, the MADD simulations do show that the separation of the forward shock and the reverse shock is smaller than the predicted in two-dimension simulations. So this is one thing that you have to take into account. The fact that 3-dimensional effects in the forward and reverse shock propagation is very important, because it will determine the physical separation between the two emissions, the thermal forward emission and the non-thermal emission in the reverse shock. And definitely, as you said, radio observations are more than necessary to separate these two regions, and probably you are going to measure different stuff over there in the polarization degree, because you will be looking to the right region that is producing the non-thermal emission, right?
Mhm.
So it works the same way, the kind of works that you guys are doing, right?
I have two short questions. I don't know if you don't know by mind, what's the column density that you expect, or maybe you know some source that calculated this for these bow shots. And because I was thinking maybe it's possible to calculate the emission with this and higher frequencies. Another question is, what measurements limit the maximum energy of the electrons?
In here, well, I don't have in mind what is in this specific source, the value of the column density. I don't know. But in general, if you can see here, back into the beginning of humanity, we would expect very different column densities. So this is good in some sense, because if you don't have a good candidate, you can choose another one, meaning that I'm pretty sure one of these guys would have a less dense color density to investigate.
Yeah,
And the second,
we should be Peloton candidates.
yeah,
Lazo observations.
and this comes again for the question of the maximum energy.
Yeah.
The maximum energy in this case is coming from the region, the size of the region and the emitting region, because you would expect to have the maximum energy limited, or by, of course, it's an estimation. We don't really know. It's an estimation, and we would have we can limit we can have a limit by equating the losses with the gain of the acceleration of electrons. And in electrons, the dominant losses are coming from synchrotron. But we also have a limit that is imposed by the size of the system with the magnetic field value there, and this is the case in this system. This is how we have the maximum energy computed, and you don't need so much electrons of very high energy to account for the observed emission. So if you have electrons of the order of 10 GeV, then it would be enough to produce significant signal at synchrotron. Hi.
I have a question about when you show the comparison with the brainstorm emission. So if you can go to this one.
Here.
Yes, you say that okay, the brainstorm dominates in a different region,
Yes.
but the intensity of the emissions of the brainstorm radiation is still very higher than the synchrotron emission.
Yeah.
So isn't that a problem, or is just in this case that?
No, I must say it's always a problem, because in this case that I am showing here, the density is very low. This Bremsstrahlung emission depends on the size of the region of this sphere, and this sphere depends on the density of the interstellar medium, and also on the radiation field of the star, because the material is ionized by photoionization of the star. So if we have a larger sphere, the problem might be even worse. And or if we have a denser region, the problem would be even worse, because the emission from the synchrotron emission would be completely hide, completely, not only in some regions. In here, we have some regions where we can actually see the non-thermal emission, but if in other case, in many cases, I would say, we won't be able to see the non-thermal emission because of the bremsstrahlung there.
But I didn't understand when it is a truly huge problem.
When?
When it isn't a problem.
The thing is that why is a problem? Where we would like to see the non-thermal emission. Why? First, because we have the observations, and we try to understand what the observations are telling us. And we're interested in non-thermal emission because having non-thermal emission implicates that we have relativistic particles there. And if we have relativistic particles, then we have more galactic sources able to accelerate and to produce cosmic rays. So this is a huge thing. And also, if the particles are there, they are going to produce non-thermal emission at X-rays and gamma rays. And this also will have another kind of galactic source, gamma ray source. That's why we are so interested in looking for the non-thermal emission and radio, because at these wavelengths, we can study this population indirectly, the population of electrons, high energy electrons. Why is a problem that there's so much density there producing bremsstrahlung? Is because if the thermal emission is very high, the non-thermal emission would be under this. So we won't be able to see. I hope this answers your question.
When you were talking about X-rays and gamma rays,
Yeah.
you mentioned on the other
Yes.
that they are really important to constrain. Could you talk a little how it works?
Yes. In this case, specifically, I do not deal with the emission expected at X-rays or gamma rays. However, when we were starting, for example, X-ray, these guys with X-rays, and we have dedicated observation with the XMM, and we observed 5 pulse shocks that we select, hoping to see some non-thermal emission as the models predicted. So we didn't see any of the non-thermal emission, and we got upper limits for that. However, we conclude that the sensitivity of XMM and all the other currently operating X-ray detectors would not be able to see different regions of emission, meaning where the non-thermal emission will dominate from the thermal emission. This is the case of X-rays. In the case of gamma rays, the people from Fermi and from Hess did this, and they took their data and they just see and look for emission in those specific regions, and they analyze the emission. And if you don't find any, you can make take some upper limits from there, because you see if the emission is up this limit, we would be able to observe it. So this is a very good upper limit, because it's coming from dedicated analysis of that specific region with that specific observatory. So we have for some sources these upper limits, and there are, I wouldn't say it would be useful for the shape of the emission, but it would be useful for the amount of emission that you can get. And if you say, okay, we need a lot of radio emission, then you have to take into account, like in the case of the observed one, I model it gamma rays. I don't have here unfortunately the result. But if you are trying to hit the amount of radio emission here, you have to be very careful not to trespass the upper limits that we have from Fermi, for example, that are very strong. Like you cannot be upper that, so you can change something. You must change something in your model. So it's really are very useful. I hope I answer your question.
Hi, Maria. I have some questions regarding the injection of the turbulence. How exactly is the injection of turbulence implemented in the code? Because you showed the value of delta V over V as one parameter.
Yes.
But what about the injection power of the turbulence and the injection scale, the wave number of the turbulence? How does it compare with the resolution of your simulations in this case? And is that to mimic the turbulence is injected in the entire box, right? Or in specific regions of the box? Because it is that turbulence in order to mimic the turbulence between the source and us, or the turbulence that should be driven directly due to the shock acceleration in the source.
I see. Okay, first, we should bear in mind that we are not interested in computing a turbulence interacting with the particles, because this is undoable for these parsec structures. Second, we are not. This is not our goal. Let's say what we've learned from people computing this polarization from the interstellar medium sources is that you need to consider that the magnetic field in the source here, because the magnetic field in the source is producing the synchrotron emission, is expected to be turbulent. And this turbulence is going to lower the degree of polarization. And this is the only purpose that we have for the turbulence. Saying that, the amount of turbulence that you would expect, like delta V over V, is not known, and it might change inside the source or in different regions of the source, etc. However, we don't know what it is. So we just consider that the amount of turbulence scales with the magnetic field solved in the MHD simulation. I hope this is clear. Saying that, we don't really need to know what are the properties of the turbulation, meaning the injection scale and so on.
So let's thank Maria again.
Thank you.
The broadcast, and we have a coffee break.
Me maté.